Welcome to Spring LIB.
There was once a record that was placed for throwing an object a very far distance. Guy threw it upward, and it made it very far, 81.2 meters far. Very, very impressive for the type of object this guy was throwing, 81.2 meters. So, and we also know one other thing, that the angle of this throwing it, that vector, this theta initial, it's equal to 45 degrees. He threw it at the perfect angle, the optimum angle, to get the most distance. And so first thing we want to do is we want to go ahead and figure out the initial velocity that the object was thrown at. So what we're going to do is we're going to use the equation that you'd use to find the horizontal range. And we'll do that here. So R equals, and this is the V initial squared. The horizontal range has quite the influence on how far, or how strong, or actually how fast it actually is launched, so that's going to have to be there. And so is the launch angle right here, mixed into that sine function. And then, of course, depends on what planet you're on, gravity. If you're on a lighter planet, this would be a lot easier. This number would be very small. This range would be greater. So this stuff all works out. But anyway, what we want to do is we want to go ahead and solve for this VI squared. So let's go ahead and isolate that and do that real quick. And naturally end up square rooting R times G divided by sine 2 theta. And you go ahead and you plug in the information you have here. R being the 81.2, that's what the R is equal to. And then G being the 9.81, and theta being the 45 degrees. And you plug that in, and you're looking at 28.2. Excellent, 28.2 meters per second. That's your initial velocity. Now, if we want to try to figure out the total time interval that the projectile was in flight, what we're going to do is we're going to use another pretty common equation here. I'm sure you guys have seen this one before here. This Vy final equals Vy initial plus acceleration in the y times t. And if we can solve this for t real quick, we get t equals Vy final minus Vy initial divided by acceleration in the y direction. And then, of course, you guys could imagine that because the projectile returns to the level from which it was launched, the final vertical velocity is then equal to the same that you'd have from earlier. So Vy final equals minus Vy initial. Go ahead, keep building this here. T equals minus Vy initial, simply using this relationship right here. Minus Vy initial divided by minus G, because gravity is, of course, pointing downward here. And when you do that, you will lose your negatives. You can combine like terms. And if you crunch through this math, oh, and of course, we have to do one last thing very quickly. We found out the velocity here a moment ago. So we have to just do 2 times, now this is the vertical direction, so it's the angle that is opposite of where our original angle was, or the component that's opposite. So because of that, we're going to want to go ahead and use sine. So 2, and I'm going to do 2 times 28.2, being this guy here, the velocity, times sine of 45. And divide this by G, which we can plug in at this point for 9.81. And you go ahead and you're going to get a T equal to 4.07 seconds. Excellent. And the last part we're just doing a little bit of a discussing on what would happen if you say you had your initial velocity in the initial part of the problem, if it increased it, if it were to increase. So as the initial angle here we use is 45 degrees. It's the optimum angle for any projectile motion. Any increase in its value will decrease the value of sine 2 theta. And since that's inversely proportional to the final initial velocity, we're definitely looking at the initial velocity increasing. And the total time in flight in part B will increase as increasing theta I, or the theta initial, will increase the final value of sine theta, and as long as the initial theta is less than 90 degrees. And the total time of flight is directly proportional to sine theta. Thanks for watching. Hope it all made sense.